Okay, so this video is about intervals of increase and decrease. So I got a picture here to kind of help you understand it all. We read this from left to right. Just like you read anything else in English, we go from left to right. So if you're going from the left to the right, if I start at this point, as I go to the right to the next point, you notice that it's higher than it was previously. If we go to the right again, it's still higher than the previous point. Go to the right again, it gets to the positive section. So you're going higher and higher from the previous point. So we say on this section of the graph is increasing. And then in this section, from this point to any point along this line, you don't rise any higher or go any lower. So because of that, we say it's constant, because it's constantly the same value. There's no interval increase, it's not decreasing, it's just flat. So it's a constant slope. And in this case, again, you notice it rises from left to right. So each point to the right is higher than the previous one. So it's an increasing interval again. And this last one, as you go to the right, each point drops down. So because of that, we say that's an interval of decrease. Whatever. So if you actually wrote this up for intervals increase and decrease, this is how we write it. So it would be increasing on the interval. From, let's say this graph, it didn't have any arrows, so you don't know it doesn't go on to infinity. It actually begins here and actually ends there as far as we know. So this graph begins at, instead of negative infinity, it actually begins at -5. And we actually put a open parenthesis on it instead of a closed bracket. We actually put a soft bracket on it because technically at that point we can draw all sorts of different slopes being one point there. So because of that, we never include it. We also put a soft bracket. So a soft bracket from -5, then it increases up to -2. So with -2, again, we use a soft bracket opposed to using a hard bracket. And it also increases on a separate interval. On this interval, it's increasing again. So from 1 to 3, union 1 to 3 is all of its increasing intervals. Its decreasing intervals, if you look at this, you begin from left to right, so our lowest decreasing interval is right here. It begins at +3. And it stops decreasing and stops the graph at 5. So it decreases on this interval. It looks kind of like ordered pair, but that's why I would title it decreasing interval. And the last one would be constant interval. So this constant interval, it begins here, ends at 1, so it's -2 to 1. So put a bracket -2 to 1, not bracket, but soft bracket. So anyway, so that's how we represent the interval increase and decrease. This kind of looks like the interval for domain and range. Same symbols, union symbols, hard brackets, soft brackets, infinity symbols sometimes. All those things look a lot alike, but we're going to distinguish. We actually can describe it by calling words increasing and decreasing. All right, moving on. I will copy any of that you didn't already know and use as a note because I'm about to erase this entire screen. All right, let's look at it this way. Suppose I gave you this parabola, this graph here. And if you notice, it has this f prime thing. Remember, f prime means derivative. Basically, what this graph is saying is, if it's decreasing, if f of x is decreasing, then its derivative is less than 0. Well, what kind of numbers are less than 0? Or negative numbers. So you ever have the derivative, and you plug in a number like 1 or 2 or 3 or so forth into that original equation, and that derivative gives you a number that's less than 0, then that means it must be decreasing on an interval. This would be the case if you didn't have a graph. In this case, you got a graph, you can clearly see that it's decreasing here. And when the derivative equals to 0, well, it's flat. There's a horizontal tangent there. And if the derivative is greater than 0, that means that it's increasing at that moment. So if you actually had just an equation and you wanted to find out whether the graph is increasing and decreasing and what's happening along that interval, you could simply take the derivative of that equation and then plug in a number that's on that interval, that's within that interval. And that number gives you an output that's negative, you know it's decreasing there. If you use output is 0, you know that's flat at that place. And it's a max or a min or inflection point. And if it's positive, you know that it's increasing along that section of the graph. Really nice thing to know, and that way we can compare it graphically and algebraically, and both answers should make sense when we compare the two. All right, let's look at some more graphs. Okay, so in this example, I'm not going to give you a graph. And the question asks to find the intervals of increase and decrease. So we're looking for both of those for the polynomial here. All right, so since I don't have a graph, it'd be nice to know the general shape of the graph. The truth of that general shape may not be it, because just because that's degree 3 doesn't mean it will have 3 turns. But it would be nice to know the general shape. So I'll get a quick sketch of the general shape. So we're going to think about this 3 ways. We can think about it graphically, algebraically, and intuitively. So let's first think about it intuitively. This is what we understand about it already. That has a negative leading coefficient and degree 3. What we understand about graphs, we know that this one should fall as it goes to the right, and it should have 2 turns. So generally, it should look something like this. Will it look like that? We don't know yet, but it generally should probably look like that. All right, so now let's think about other things we know about this graph. We know that if the derivative is negative, we know it's decreasing. So let's first find the derivative. So the derivative of this would be y prime is equal to negative 3x squared plus 2 times 5 as is 5x to the first plus derivative of this is 2, derivative of that 0. So y prime comes up to this nice little neat quadratic equation. I'm willing to bet I can factor it or solve with quadratic formula. So I'm going to try to see if I can factor it to find the zeros for it, so I can figure out where those max and mins would occur. So I factored it. I don't need the leading coefficient to be negative, so I'll factor out -1 from everything. So -1 comes out, making this positive 3x squared, subtract 5x, subtract 2, and I'm going to make it equal to 0, because I'm trying to see where the max and min would occur if they actually occur, or inflection points. So you factor this, you can distribute that in, and you wind up having -1, and then x squared, subtract 5x, subtract 6, and yeah, that's factorable. -1, and that's going to be x subtract 6, x plus 1. You got to divide those each by 3. So what we have is 0 equals to -1. And so use x subtract 2, x plus 1/3, or 3x plus 1. I'm going to leave it at x plus 1/3 because I want to solve it anyway. So I know that x subtract 2 equals 0, x plus 1/3 equals 0, and x has to be 2, or x has to be -1/3. So I know at those 2 places, something special happens. It's either going to be a max or a min or an inflection point. So it's really nice to know that at 2, something's going to happen, and at -1/3, something is going to happen. Still don't know if that actually is going to match what we have here, but I do know those are definitely special places. All right, so to investigate this further, I'm going to need more space. So I'm going to have to erase pretty much all of this. So if you don't have any of this down, or you didn't do this on your own or whatever, pause the video and copy down my notes for it, and then after you finish, hit play, and I'm going to have some new things up. So go ahead, pause it. All right, so we know that these 2 both are horizontal tangents. And we do still need the derivative equation, so rewrite that again. All right, so what I really want to know is, when is my derivative negative? I think it's negative to the left of -1/3. Don't really know for certain though. So I'm going to choose a number to the left of -1/3. A number to the left of there is -1. So in my derivative equation, I'm going to see what happens at -1. So y prime at -1 is -3 times -1 squared plus 5 times -1 plus 2. So it gives you -3 subtract 5 plus 2, which is -8 plus 2, which is -6. So I know for certain that it's definitely, the derivative is actually negative here. So I know it's decreasing on that interval. I know that for certain. So I know from negative infinity, it's decreasing. Decreasing from negative infinity up to -1/3. That's my horizontal tangent. It may be an inflection point, but we'll see. All right, so anyway, after that place is definitely decreasing there. So it may be decreasing again. I'm thinking it's probably going to be decreasing on the right side there. So let's go ahead and check. To the right of 2, it's probably going to be decreasing. Oh yeah. To know if that was an inflection point, I would test the point in between here. And if it was 0 or positive or whatever, it would tell me whether or not it's an inflection point. If it was negative again, that means it went flat and then it went down again. But if it's positive, that means it turned directions. So let's go ahead and test the point here before we go further. All right, so a good easy number in between here to choose would be like 0. Again, if it's negative, that means it still is going down. And if it's positive, that means it changed directions. And it wasn't an inflection point, it really wasn't minimum. All right, so I need this equation again. I want to test that equation at 0. So at y prime equals -3x squared plus 5x plus 2. At 0, basically make all the x's go away. So this becomes 0, that becomes 0, and you get y prime equals 2. So if that's the case, it's definitely positive. So it's definitely increasing here. All right, so I know it's definitely increasing on that interval. All right, so this is an increasing interval. Increasing. I'm just going to make a note to self. It's got one interval left to check, and once I have that, I can finish this. So my last one to check is here, to the right of 2. So I need some space to check it. So I guess I'll put it up here. So y prime equals a -3 times a number to the right of 2. I'll just say 3. So 3 squared plus 5 times 3 plus 2. So this is -3 times 9 is -27 plus 15 plus 2. So that's -12 plus 2 is -10. That's definitely negative. So it's definitely decreasing here. It's decreasing again. So it's decreasing from negative infinity to the -1/3. Then at 2, it begins decreasing again. So it decreases again from 2, and then it decreases forever to positive infinity. So this is my decreasing interval, which is what we kind of thought it was. And that leaves my increasing interval to be this. Make it brown. So it's increasing from -1/3 to 2. That's my increasing interval. And that's it. We found out what it was graphically. Well, we found out what it was intuitively and algebraically. If we want to find out what it was graphically, we simply graph the original. We cheated, I guess, or did it faster. I just graphed the original to figure out what it really was doing on those sections, which is perfectly fine. You can't do that. Anyway, those are all the ways you can do it. That's how you can use intervals increase and decrease and find out whether it's increasing and decreasing on those intervals. That's all I have. Good luck.